Welcome. In this lecture, we'll continue the LD steel making, and here we'll discuss the oxygen lens, jet action, and decarburization. So first we'll discuss about the lens characteristics. Oxygen lens has a especially the nozzle is very special. I need to know about that. And then we'll talk about the jet action, and that is the interaction of the oxygen jet with the metal bath, and that interaction we need to understand, that is called the jet action. And obviously a very important reaction called decarburization. Decarburization not only that is the reducing the carbon in the process, decarburization also has a role to play, because decarburization basically produces in situ CO and in the slag, and that basically forms the foam as I just discussed, and the emulsion. It stabilizes the foam as well as the emulsion. So decarburization has a very important role in LD steel making, because the decarburization has to continue to the end such that you can keep the foam and emulsion stabilized to the end of the process, because in the emulsion only you have a tremendous surface area in the slag-metal interfacial area, and where kinetics is fast because of that. So decarburization reaction has a very special importance into LD steel making. Okay, now let us first discuss with the oxygen lens. You can see this is the oxygen lens, and oxygen comes to this annular portion, and you can find here basically the cooling arrangement is there. Basically you have water flow, one inlet and outlet, such that the nozzle remains cools. And another feature is that you can find, so you can see that and nozzle also, there is a special nozzle is there. It is not a cylindrical nozzle. You can find there is a convergent section and there is a divergent section. It's convergent and divergent. This way the nozzle is actually, if you see it here, this type of thing somewhat. Here if we draw it, okay. This is the convergent section. It is the throat, it's called the throat, and this is the divergent section, divergence. So gas comes like that and go out. So the nozzle, it is the special nozzle, it's the convergent. Initially it is convergent, you can see from here also, initially it is convergent, this area, here it is converging and then again diverging nozzle you can find. So this type, and there is a throat also in between, the cylindrical portion, and then it is diverging. So this type of nozzle, it is also called the D-level nozzle, right? Okay. So uses a convergent divergent nozzle, and also called the D-level nozzle, because a cylindrical nozzle, because we need to you can see here is supersonic jet is forming. Basically by convergent divergent nozzle we can accelerate the gas to a supersonic speed, that is the speed greater than the speed of the sound, right? So that is called the supersonic speed. We can pushes the air at a very high velocity, pushes the oxygen at a very high velocity from this nozzle. But in case of, if I use a cylindrical nozzle, then I cannot push the oxygen at a very high velocity. What happens is that in case of the cylindrical nozzle, what happens, the gas, because if you push the gas at a very high pressure, you have to give a very high pressure at the upstream point, and when the gas come out, it also come out at a very high speed, a very high with pressure. So from cylindrical nozzle, when the gas is coming out, it is expected that it will come out with a very large pressure. So, and the ambient, so what happens, this is the large pressure oxygen jet then interact with the 1 atmospheric ambient air, right? And as a result, most of the energy get dissipated in the form of shock waves, what is called the shock waves, in case of the cylindrical nozzle. But in case of the convergent divergent nozzle, because of this design, when the gas is come out from here, and the pressure of the gas, there is the pressure of oxygen, when it is coming out of the diverging section, it can be controlled to 1 atmospheric pressure. By proper design of the length and divergent section length and all these things, you can get a very high speed oxygen jet emerging out from the nozzle at an atmospheric pressure. As a result, it will not interact with the ambient air, and the oxygen will accelerate with the same speed, in the supersonic speed. So, supersonic jet will come out at around 1 atmospheric pressure. So, the jet will progress through the atmosphere. Obviously, it will enter in the surrounding atmosphere like this. Okay, so this is the advantage. So, you are basically using a convergent divergent nozzle, and that has the capability of accelerating the oxygen or producing an oxygen jet at supersonic speed. And when the gas will come out of the convergent divergent nozzle, its pressure is almost equal to the ambient pressure. That's why the interaction with the atmosphere is not very large. As a result, shock wave generation is not possible here. So, your energy distribution is not there. But when such high pressure oxygen jet, when the oxygen, if you want to produce the oxygen jet through a cylindrical nozzle, and they will come out with a very high pressure, and oxygen will come out high pressure, and it will dissipate energy by shock wave generation. So, this is the thing, it can accelerate the gas to a supersonic speed through the atmosphere. That is the most advantage of this, using this convergent divergent nozzle. And some characteristic of the oxygen jet you must see. First thing is that supersonic core Mach number is 2.5. What is this Mach number? Mach number is velocity of the oxygen jet divided by the velocity of the sound, and that is 2.5. That is, the velocity of oxygen jet is 2.5 that of the velocity of the sound, right? So, supersonic core, that is also not, then when the oxygen is coming out from here, its velocity is supersonic velocity, and find you can, it is called the supersonic core. Why? Because when the oxygen jet is moving through the atmosphere, it entrains lot of air into it, and that's why this portion, this is also a jet, this is a complete jet you can find, but portion of this jet becomes subsonic, because there the velocity becomes reduced, because you are entraining lot of air into it. So, you are increasing the mass, as a result velocity is decreasing. So, this is the subsonic portion, and this region is called the supersonic portion, and supersonic portion you can see, and it extends. And what is the length of this supersonic core? It has been found that it is around 15 times that of the nozzle exit diameter, okay. So, 15 times that of the nozzle diameter. So, it extends up to that, right. So, this is one of the important characteristics. Second characteristic is that is the jet entrainment causes lateral expansion, where the jet becomes subsonic, because the entrainment, air entrainment is there, and it becomes subsonic, okay. And there is a lateral expansion of the oxygen jet, because after taking a lot of air into it. So, this is the thing, and it becomes subsonic. This is the white portion is the subsonic portion. Typical oxygen pressure used in the upstream region here, basically approximately 1 megapascal of oxygen pressure is used, okay, to produce this supersonic jet. And this is about the nozzle. And one thing is that we use the multi-hole nozzles, right? We use the multi-hole nozzle to increase the bath impact area for large capacity furnace. For large capacity furnace, it is not only one just nozzle. You use the multi-hole nozzle, and if I draw the plan view of the nozzle, it will look like this. This is the nozzle, and you have several convergent divergent nozzles are there inside it. So, number of holes, this is all are convergent divergent nozzle, 1, 2, 3, 4, 5, 6, suppose 6 convergent divergent nozzles are there, and the nozzles are configured in such a way such that they do not overlap with each other, because they will be independent, and then basically increase the total impact area of the bath. Other single nozzle have this much impact area. If you have 6 nozzle, and then it will have more impact area of the bath, and that is required for big capacity furnace, okay. So, there you use the multi nozzles are used, okay. In the lens you have a single lens, but you use not a one nozzle, you have multi nozzle system, such that your impact of the oxygen jet with the steel bath become maximized. Now let us consider this the flow through the D-level nozzle. Let us see how basically a D-level nozzle produces supersonic core. Not only that, supersonic, the oxygen jet comes out at supersonic velocity almost at 1 ambient pressure. Okay. So this is the convergent divergent nozzle, just have talked about. It has three portions. One is called the convergent section, then you have a throat which is basically a cylindrical section, and then there is the diverging section where basically you can find out is the diverging, there is the nozzle is diverging out, right. Now let us see, okay, so equation of momentum for one dimensional compressible flow, basically how, let us see how this type of nozzle produces a supersonic oxygen jet, okay, through this nozzle, and why it emerge at 1 atmospheric pressure. Okay, if we see, that is the incompressible, that is the equation of momentum of one dimensional incompressible flow. So if you consider the momentum equation for one dimensional incompressible flow, we can write like this. Basically, if you consider the that is your, this is, you have the Bernoulli's equation, you have in this case only the pressure head will be there and the kinetic head, there is no gravity head because it is horizontal. Okay, so you can consider that is the pressure, basically here anyway the gravity will not be very important here because it is a gas, it does not make a difference with the height. So here basically the pressure drop across this nozzle, anywhere, any section, pressure drop will be equal to the rate of change of momentum across these 2 points. If I consider this point to this point, what is the pressure drop is basically equal to the change in momentum, rate of momentum change. So this is basically the rate of momentum change that is equal to the pressure drop. Okay. So this is simply for one dimensional compressible flow is like this. An equation of continuity you can write like this. Basically equation of continuity, you have d of, that is the rate of change of rho ua, basically rho ua, that is basically d of rho ua differentiation. If you can do that thing, that is the continuity equation. So d of this is equal to 0, that is the rate of change of, this is the mass at any point. If you consider this point and this point, so rho ua 1 is equal to rho ua 2. Since it is a compressible flow, we have to consider rho ua. Rho ua is the total mass rate, that is the mass rate. So mass rate at this point should be equal to the mass, because mass cannot be accumulated, that is the continuity equation. Or you can write d of rho ua, that is 0, and if you expand this and divide it by throughout rho ua, you will get this thing, because you can just expand. So then this is the continuity equation what you will get, and equation of continuity, and then you can have the relationship. Velocity of sound is basically defined as rate of change of pressure with density, and square root of that, that is the definition of velocity. And then if you combine all these three, you can get a combined equation like this, that is the du by u. Bar means basically the average velocity, because in a cylindrical any velocity there is a distribution across the radius. In any cylindrical section there is a distribution across the radius, so u bar basically represent the average velocity. So rate change in average velocity, that is du by u bar is equal to m square minus 1 is equal to dA by a. So now let us consider this, all this section. First section, if you consider for a converging section, let us consider this is the converging section, and dA is negative. Why? Because your A is high, here A is less. So because dA A2, here if you consider A2 minus A1 is negative, obviously in convergence section dA is negative. So now if you want, that is the, you want to accelerate the gas, if you want to accelerate the gas, then du has to be positive, because u2 minus u1 should be positive. So this is positive and this is negative, this is negative, and if you want to make du positive, obviously m square minus 1 has to be negative. So m square minus 1, if it is negative, then you obviously get, that is the m square minus 1 should be less than 1, so m square, m should be less than 1. So you are getting that thing. So if, since dA is negative and you want that gas should accelerate, that is du should be positive, so your m has to be negative. So, in a convergence section, if you want to have an accelerating gas, in that case, the velocity should be subsonic. M should be less than 1. M is basically Mach number. M is velocity of gas divided by velocity of sound. So, velocity of gas should be less than velocity of sound, that is, it will be subsonic, right? Okay. So, this is okay. Now, for a diverging converging section, it is okay. At cylindrical portion, what will happen? Cylindrical portion, dA is 0, dA is 0. So, as a result, m square minus 1 has to be 0, because du by u, that is the du cannot be 0, right? So, m square minus 1 is equal to 0. So, m is equal to 1. So, here you will attain the velocity of the sound, that is the gas velocity will attain the velocity of the sound, because Mach number is equal to 1. So, here the velocity of subsonic, and then in the throat region the velocity becomes sonic velocity, right? Gas velocity becomes sonic. Now, in the diverging section, what happens is that, let us see, at the throat, and then at diverging section, what happens? Diverging section, obviously dA is positive, because A2 is greater than A1. So, here dA is positive, and if you want to make the du to be positive, then m square minus 1 has to be positive. If m square minus is greater than 0, so m is greater than 1. So, in this case, it become a supersonic. Okay. So, it becomes a supersonic. So, m is greater than 1, it become a supersonic jet. So, we want to accelerate it, that is why. Otherwise, the fluid will come to rest. If m square is less than 1, then because this is positive and this is positive, m square minus 1 cannot be basically negative. Okay. So, this is the thing. So, m will be positive, here m is greater than 1. So, here the velocity up to this is subsonic, then sonic, and in this region it will be supersonic. So, velocity of the gas will exceed the velocity of the sound in this region, and as it goes more and more distance, because you can find, that is the thing. And the length of the ds section, now think is how we will select the length of the ds section, because as the gas is flowing and as the gas is accelerating, so its velocity is increasing. So, as a result, its pressure will be decreasing. So, when the gas is moving in this direction, it is accelerating, its pressure will correspondingly decrease, and you can have a ds section, length of the ds section you can design in such a way such that when the gas emerges from the exit, its pressure become exactly equal to the 1 atmospheric pressure. So, based on design, you can do what will be the length of the ds section based on when the pressure of the oxygen jet at the exit of the ds section should be equal to the 1 atmospheric pressure. Then only you can effectively project the gas, okay, at supersonic velocity towards the oxygen bath, or towards the liquid bath. Okay, so this is the thing. So, that is the way you can accelerate to this. Now, let us come to this jet action. Now, this is the D-level nozzle. So, you can understand that in D-level nozzle or the convergent divergent type of nozzle, basically you can generate a oxygen jet with supersonic velocity, and with the proper design of the ds section also you can control the pressure of the gas that is emitting in the atmosphere. So, its pressure you can make it exactly 1 atmospheric pressure at the exit of the ds section. Okay. So, let us consider the jet action now. Now, this is we have generated supersonic jet, and then a supersonic core along with the subsonic core, finally it hits the bath and make an impact. Okay. Now, we need to see, that is the action of the gas jet on the liquid surface produces 3 distinct regimes with increase in the JFN. Something is called the jet force number, that is, if you want to understand, that is what is the impact of the oxygen jet on the liquid bath, you should have some number to quantify the impact, that is called the jet force number, and it is defined like this: upstream gas pressure, that is approximately 1 megapascal, as I said, multiplied by the nozzle throat diameter divided by the height of the nozzle, that is the how close or away from the bath the nozzle is. This is the, now gas pressure is constant and it is a design, both of the above two parameters, numerator, both the parameters are design specific and it is constant. What is in your hand is the height of the nozzle, that is where will keep the oxygen jet, that is in your height. So thing is that if you have a bath here, this is the bath, and then this is the oxygen lens. So this distance you can height of the nozzle, this is called the height of the nozzle, and this is the height of the nozzle and which you can control. This is the height of the nozzle. Okay, so you can push it up and down, that is that you can take the nozzle up and down and you can change the value of H. Okay, and you can control the JFN. So the when H basically decreases, JFN increases. That is, when the H decreases, your JFN increases. Obviously jet force number increases and it makes a more impact on the bath, right? So that is the way the JFN number comes into picture. And now dimpling, now there are 3 dims, because depending on jet force number you can produce the 3 dims. One is called the dimpling with a slight surface depression. Now here is the nozzle, you can find this much is there, and then whatever is the force, that is it can forms a dimple, small dimple, and lot of splashing of the liquid droplets away from it. Okay, so a very slight depression is there. In this case is a slight depression and the liquid droplets are ejected across this, and then they can hit basically the refractory wall. So this is not a very good condition. So dimpling, okay, so liquid droplets can be ejected and then they can directly hit the refractory wall there. And then if you increase the jet force number little bit, now you are increasing the jet force number, then you get what is called splashing with shallow depression. It is there, it is called the splashing condition with the shallow depression. It was the dimpling, now we had it is the splashing with the shallow depression. Depression is there, here it was a slight surface depression, here it is the depression is more compared to the dimpling. Splashing, in case of the splashing, your depression is little more, depression is more, and here you can, and another thing is there, and finally you can have, if you further increase the JFN number, then the penetration with reduction of outwardly directed splash. Now you can find these 3, dimpling, splashing, and penetration. In case of the dimpling, the surface depression is very less. In case of the splashing, the surface depression is much higher compared to the dimpling case. And in case of the penetration, here you can find that is they form a big crater, actually lot of big crater they form on the surface, and your reduction of outwardly, that is this type of, this is basically the liquid droplets, and liquid droplets are ejected away in this way. Now here you can find, here the liquid droplets are ejecting with a very small angle to the horizontal, and then this droplet can directly hit the refractory wall. In this case they are moving little off compared to that, and they will go through the slag phase and maybe damp there in the slag phase. Okay, so here basically you can find they are moving little off. And in case of penetration, what you can find is that in this case the liquid droplet, that is the droplets are moving this way, so they are not splashing away. So reduction of outwardly directed splash, you are just reducing the splashing thing, that is the liquid droplet here it is little move over, finally they will go and reflect into the, that is the hit the refractory wall and erode the refractory wall. But in this case you can find all the what is the droplet will basically move to the interior of the furnace, right, through the slag phase they will move, and then this thing. Okay, so that is the thing, there is the penetration with reduction of outwardly directed splash. So this type of depending on the JFN you can produce a, that is the penetration with reduction of outwardly directly splash. As we are discussing, in this case there is the splashing, there is will be reduced completely, and all the metal droplet will go this direction towards the center of the earth in the emulsion phase. Basically they will be, this metal droplet will be ejected into the emulsion phase directly, okay, rather than they are going towards the refractory wall, right. So this is a very good thing, but this penetration, but that is the last two types behavior usually observed. You can have this or this thing. This is the mostly observed, but it has two categories that we will discuss, because if your GFN is little less in this case, then the rate of generation of FeO, what is there? By controlling the GFN, what you can do is that, first of all, is the splashing you want to reduce it. That is, this type of splashing is not desirable. You try to eject the metal droplet towards the emulsion inside the furnace, not towards the refractory. Okay, that is first thing. And second thing is that, depending on the GFN, you can produce the big crater, small crater also. And depending on the GFN, what happens is that your two parameters are there. One, that if you increase the GFN, your rate of decarburization also increases. Why it increases? Because you are increasing the GFN increases, means your partial pressure of oxygen is increasing, because you are giving the more pressure on the liquid surface. So oxygen partial pressure become more. So as a result, your decarburization rate also become high. Okay. And at the same time, you are generating the oxygen, that is, you are first oxidizing the iron also, you are generating the FeO also, and your decarburization, both are going on. But if your GFN is very high, and then the case may come where the rate of decarburization is more compared to the rate of generation of FeO, because in that case directly oxygen can be dissolved and carbon can react, and directly it can form the carbon monoxide, not necessarily through the FeO, there is the carbon will react. Okay, because the partial pressure of oxygen is so high, that is, the oxygen can directly dissolve and it react with the carbon, forming the CO gas. Okay, and in that case, that is, the rate of decarburization may be higher than the rate of formation of FeO. So in that case, what happens sometimes, that is, the slag become very dry, because it is the FeO that basically contribute to form the low melting eutectics. So if you have significant amount of FeO, the slag fluidity really increases, because it forms a lot of low temperature eutectics. So if FeO decreases into the slag, then it becomes viscous and dry. That is called the drying of slag, and that is not a good at all, because if the slag is viscous or dried, then the mass transfer in the slag will be very less. So you cannot effectively transfer the impurities to the slag phase. So that is called the drying. So if GFN is very high and the crater is very big, in that case rate of decarburization can be more than that of the FeO formation, and that condition is called that give rise to the drying situation, drying of the slag, and that is called the hard blow, right? That is called a hard blow. And people sometimes do it, and only to increase the decarburization to a very faster rate. Okay, otherwise it is not justified. And in that case, you can blow little softer. You can make a very quite soft blow. In case of the soft blow, what happens? You decrease the GFN by taking away the lance from the bath. So you can decrease the GFN, and then when the GFN decreases, then your rate of formation of FeO become more than that of decarburization. That is, you can build up the FeO into the slag, and that is sometimes is required. I will talk about that thing. That is the slag practice people do. You build up the FeO by suppressing the decarburization, and this is mainly done when you have large amount of impurity like phosphorus in the liquid iron, large amount of phosphorus. So what you have to do, you have to continue with the carbon to the end of refining. In that case, initially you do some soft blowing such that you build up the FeO, and because the FeO buildup is very important for the CO dissolution, calcium oxide dissolution. And also calcium do not dissolve immediately, some temperature is required. So when after some time, when the temperature is high, FeO is significant, CO easily dissolved, make the basic slag, and then the phosphorus renewable starts. Anyway, all these things I will discuss. So soft blowing is good for treating a very high phosphorus steel sometimes, and that will do, because initially you need to build up the FeO into the slag. Okay, that is called the soft blow. Now let us come to the kinetics of decarburization. This is very important. You can see that the rate of decarburization, that is the percentage of carbon per minute with the blowing oxygen blowing time, and you can see the curve is like this. So that means here the decarburization rate, that is it is the decarburization rate basically, dCdt, decarburization rate, that is the percentage C per minute. So you can see initially it is first you are removing the decarburization, so decarburization rate increases. Okay, it can increase this way or that way anyway, but decarburization rate increases and then it stabilizes here. This is called the steady state, and then the decarburization rate decreases. You can see the rate decreases and finally becomes 0. So this is a typical decarburization curve. Okay. Now if I want to understand these three regimes, one is this regime and two is the steady state regime and three is the third regime. Okay. Let's see first regime. Regime 1 is called the decarburization is controlled by the oxygen mass transfer. Here basically the rate of decarburization is controlled by oxygen mass transfer. That means you have blowing practice has a role to play, because initially bath has a lot of carbon, it is the oxygen. So initially when you are blowing it, that is you are just supplying the oxygen, you are forming FO and then FO decarburization, whatever it may be. So basically you are supplying the oxygen. So then obviously rate of supply of oxygen is less compared to the rate of supply of carbon, because you have plenty of carbon in the liquid bath and it is the oxygen supply that will control the decarburization rate. So here you have the blowing practice as a role to play, because by changing the lens height up and down, you can change the JFN number. As a result, you can increase the decarburization or decrease the decarburization rate, because you can change the partial pressure of oxygen and it will respond. So initial rate may be like this, right? Whatever is this is rate. It can go this way also, it can go this way and then it can come down, or it can go this way also, it can be further. That is what I am trying to say is that it can go like this also, it can go like this, it can go like this also. So in this case, that is the decarburization rate initially is very fast. So if you do the hard blow, then your carbon decarburization rate will be very fast. If you make a soft blow, the decarburization rate may be like this, or this is a normal case. So thing is that depending on what JFN number, that is the JFN number has a role to play for initial decarburization rate. You have control. So initially you can control the rate of decarburization by blowing practice. But here what happens in the steady state situation, what happens in the steady state situation, your rate of oxygen supply become equal to the rate of carbon supply. Now carbon is depleting now. So but still here sufficient carbon is there, whatever the rate at which you are supplying the oxygen and the rate of carbon supply is also sufficient. So both rate become equal and then it comes to a steady state situation like this. Okay. So steady state, and then what happens after this point in the third regime, it is the carbon, because the bath now become very depleted in carbon become very less. So it is not the oxygen supply no more, because now after some blowing time you have a lot of FU into the bath, so FU into the slag, so your oxygen supply is not a problem also, plus your oxygen jet is there. So oxygen supply is plenty. Now you are depleting in the carbon. So it is the carbon that is the mass transfer that basically controls the overall process here. So here blowing practice had no role to play, and only blowing practice has a role to play in the first regime. So during the initial blow you can have a jet up and down and you can control it. That has a very great effect. So that I say that is the two regime. In this regime 1 you have a hard blowing and the soft blow, as I said. So hard blowing, if you have a JFN number is high, but problem is there, the drying of decarburization rate is very high, but the drying of slag is a problem. Okay. So slag can get dried off, dry slag. Okay. So this thing is there, you can call it, you can write, this is the DC decarburization rate is very high, DCDT. This is very high, hard blowing, and but your slag can dry slag, but you have a dry slag. You can have a dry slag. Okay, that is the two things. The decarburization rate will be very high, but you may have a dry slag. And soft blowing, basically you have in case of the soft blowing, you have DCDT less. Okay, so DCDT less, and you have FU buildup in the slag, because rate of generation of FU is much greater than rate of decarburization. So you can build up the FU into the slag, and DCDT is usually less, much less in case of the soft blowing. That is the two things you can understand. Okay. Then you come the regime 2, here the decarburization in the steady state, as I said, and then you have Regime 3 decarburization, that is the controlled by the carbon supply, as I said, and blowing practice has no role to play. So, this is the kinetics of decarburization. Now, decarburization and the sloughing phenomena is very important phenomena. What is called a sloughing? In LD furnace, sloughing is the phenomena where basically the emulsion emerges out of the ladle mouth. That is called the sloughing. Obviously, you do not want the sloughing because sloughing is a very cumbersome phenomena, and also you loses lot of iron, right. The sloughing is a phenomena when emulsion comes out of the mouth of LD causing iron loss. That is called the thing. And then you can find there are two heats from the industrial plant. So, you can see that is the this is a normal heat, heat A, you can say, that is the first stage, regime 1, that is the normal, that is the decarburization rate increases and then it is almost steady state and then coming down. And there is another heat from industry itself that is not normal. You can find here the decarburization is very slow, okay, and suddenly there is a sudden jump in the decarburization rate. Here in this location there is a sudden jump in the decarburization and then it come to a steady state and come down. And in this case basically the sloughing take place. Why? Because if you suddenly increase the decarburization, then suddenly the foam will increase, right, increase in height, and then it can come out of the ladle mouth. Emulsion can come out because it can exceed the height of the foam, can exceed the height of the ladle, and then the foam will come out, foam and the emulsion come out. So, that is called the sloughing stage. So, if you have a sudden increase in the decarburization rate in the initial period, that is when you have the blowing practice as a role to play, okay, then improper blowing practice can lead to a sloughing. Thing is that you have decarburization less and suddenly you want that I have to reduce the carbon, I hard blow it, then it can happen. But it can also happen due to improper mixing in the bath. Usually the ladle, you can see the LD vessel, the upper part is nicely mixed up, but the lower part of the vessel is not mixed up because the momentum of the oxygen jet does not reach significantly to the lower part of the bath. As a result, there the velocity becomes less. So, what happens? They are not properly mixed up. So, as a result, the carbon may be accumulated into the lower part, they remain, they do not participate in the reaction too much. And suddenly, when some liquid from the lower part comes up and comes in the upper part and participate into the decarburization and then goes into the emulsion phase. So, suddenly when the liquid from the bottom part goes to the emulsion phase and then a sudden jump into the decarburization can take place. So, if you do not have a proper mixing, then sometimes it can happen. There is a liquid from the lower part goes into the emulsion. They first liquid are moving in the lower part and some packet comes and join the upper part of the vessel and then from there they join the emulsion phase and then sudden burst in the decarburization rate, and that can give rise to the sloughing phenomena, right. So, as I said, in case of the heat B, decarburization is slower initially and then after 8 minutes decarburization pick up suddenly leading to sloughing. And the reasons are, one is the blowing practice, because here you can do the hard blow suddenly, you want to remove the carbon first, you can do that, but if you want to do it fast, it will not be fast, but you can lead to a sloughing. And second thing is the insufficient mixing. As I said, I will talk about that thing when I will come to the hybrid blowing practice in LD, that insufficient mixing also can lead to a problem. So, that part I will come to later on. And then so lower part, so some liquid from the lower part when suddenly joined to the emulsion phase and then they give a burst into the decarburization rate, because those are rich in carbon, because their carbon has not been utilized, lower part of the vessel has not been utilized because of lack of mixing, they are not joining the upper part. So, they are very rich. So, when they suddenly come into the emulsion phase, then there is a burst in decarburization and sloughing phenomena obviously will take place. Okay. So, these are the reference, and then conclusion we can say, that is the first thing is that convergent divergent nodal, that is the D level nodal is used in LD lens to accelerate the oxygen jet at supersonic velocity and without any shock wave generation, because when the jet emerges from the nozzle end, its pressure is almost equal to the atmospheric pressure. So, convergent divergent type of nozzle is required. That nozzle only ensure emergence of a supersonic jet, oxygen jet with pressure equivalent to the atmospheric pressure without doing any shock wave generation. And then depending on the jet action, as I said, you can quantify the jet action by JFN number, and JFN number you can control it basically by the height of the lens over the liquid surface. Okay. And depending on the jet force number, there is the what is the intensity of impact. Depending on intensity of impact, various scatters can form. It can form a very mild to the very deep, okay, on the liquid surface. And they control basically the rate of decarburization, the slag type also, initial, what type of slag you want to develop. That is, the slag evolution also can be controlled by this blowing practice. Suppose you want to initially form a very FeO rich slag, then you have to make a soft blow such that your decarburization is less and you are building up the FeO, right? And if you want to decarburize fast, then you can make a hard blow. You can increase the JFN by lowering the length, and then you can decarburize at a very fast rate. And in that case, rate of decarburization is greater than the FeO buildup in the slag. Okay. So that you can do, but you have to be cautious, because if you do it for a long time, then the slag can be dried up because of lack of FeO into the slag. Okay. And then kinetics of decarburization is categorized in 3 stages. As I said, in the first stage is basically oxygen mass transfer control, because initially you have plenty of carbon into the hot metal. So initially the rate of decarburization is controlled by supply of oxygen. So in the initial part, in that part, there is the decarburization rate increases steadily, and then you can control the decarburization rate. How fast you want to increase or decrease that thing will depend on your blowing practice. So blowing practice has a role to play, and it is followed by a steady state decarburization rate when the rate of supply and oxygen become equal. And in the third stage, it is the transfer of the mass transport of the carbon that basically controls the overall decarburization rate, right? And finally, so this is decarburization rate is very important, and as I said, into the LD refining process, and your blowing practice has a role to play in the initial period. So you have to be very cautious in the initial period. Your lancing technique or the blowing practice should be accurate, depending on what type of slag you want to evolve. For treating what type of hot metal is coming, you can evolve a slag according to your need by changing the blowing practice, right? And sloping in LD may take place. Sloping means, as I say, sloping means basically when the emulsion comes out of the LD mouth, and that is making a lot of loss, and also it is becomes a very cumbersome process. Sloping becomes a very cumbersome thing. So thing is that you can stop the sloping by, it can happen due to improper blowing practice or insufficient mixing in the bath. If the bath is not properly mixed, then also it can happen, or because of improper blowing practice. Okay, thank you very much.